Hi folks, we're going to take a look at the lesson on developing what are called the compound angle formulas. Okay, so these are a set of identities that allow us to determine the cos or sine of the sum of two angles, or the difference of two angles. And we're going to see that that's going to lead us to some other nice relationships. So the first thing, now what you might want to do throughout this video is just stop it and try to work on certain things on your own, and then I will take them up. So the first thing that I'd like you to do, and I want you to think in terms of right angle triangles, is I'd like you to write the formula for the opposite and adjacent sides in a right angle triangle using these variables here. Okay, now I'll give you a hint. I don't want you to use tangent to determine either of those formulas. So you can just stop the video now and just write those out. Shouldn't take you too long. All right, so we're back and let's take a look at this here. So again, if I've got some right angle triangle, okay, this is my angle theta, and of course this is my opposite side, this is my hypotenuse side, and this is my adjacent side. And so what we have is if we take sine of theta, well, what do we get? We get opposite over hypotenuse. So that means that the opposite side can be written as the hypotenuse times sine of theta. All right. And if we take cosine of theta, of course, that's adjacent over hypotenuse. And so we can write a formula for the adjacent side as the hypotenuse times cosine of theta. Now you might ask yourself, well, that's pretty standard stuff, nothing too hard there. But the reason why I want to write it out is because I'm going to be using this constantly in our demonstration. All right. So now that we have that, let's take a look at the setup that we have. So we've got this rectangle, and it's set up so that it has this inscribed right angle triangle with a hypotenuse that's equal to 1 unit. Okay, and we call this angle, this acute angle inside the right angle triangle, A, and then this other angle made with the base of the rectangle, we call that B. All right. So first of all, we have to accept that while this is going to be a pretty nice and straightforward demonstration, it really does only demonstrate these properties for acute angles. Okay, now it doesn't necessarily just describe them for these particular acute angles, because what I could do is just change the shape and size of the rectangle and still create a triangle that has a hypotenuse of 1, but not necessarily the same opposite and adjacent sides, and so A and B would be different angles. But the fact is that this is not actually a proof of these properties for all angles, but it's a demonstration for acute angles, and you just sort of have to trust that it does generalize to any pair of angles. All right, so this is what our goal is. Our goal is to try to indicate all the angles in all the triangles and all the side lengths in all the triangles. So here notice we've got 1, 2, 3, 4 triangles. Okay, and we're going to try to fill in all the possible details. And I'll get you started, and then what I'm going to suggest is that you try to do as much of it as you can before we come back together. So let's start with the right angle triangle that's inscribed here. All right, so here the angle is A, and I know the hypotenuse is 1. So if I want to determine an expression for the opposite side, well, let's remember, opposite is just going to be the hypotenuse times sine of the angle. Well, the hypotenuse is 1 times sine of the angle, that's just A. So this opposite side can be written as sine A. And the adjacent side is just the hypotenuse times the cosine of the angle. So again, the hypotenuse is 1, angle is A, so this side here can be written as cos A. All right, so the order which I'm going to suggest you go is now you move down to this triangle below, then move to this small triangle at the end, and then at the end, and then finally move to the large triangle above. Now, just to give you a little heads up as to how you proceed, now all of a sudden you have another right angle triangle for which you know the hypotenuse, except now the hypotenuse of this right angle triangle is cos A. So fill out the opposite and adjacent sides. One little thing you are going to have to do is, once you get to these two triangles, you don't have the angles inside of them. So you can find them, but you have to do a bit of justification for finding those angles. Okay, so this would be a good time to stop the video and see how much of this you can fill out, and then we'll come back together and go through it. Okay, so we'll see you back in a little bit. All right, we are back. So now we're going to move to fill out the rest of this diagram. So let's start with this right angle triangle here. So the opposite side, remember, is the hypotenuse. So cos A times sine of the angle. So this is going to be cos A times the sine of B. Okay. The adjacent side is going to be the hypotenuse times cos of the angle. So hypotenuse is cos A times cos of the angle, cos B. Okay, so we're done with this one here. So let's move on to this small triangle. Now the first thing that we have to figure out is an angle inside this small triangle. Okay, so I'm going to have to do a little bit of work here. So I do notice that this is a right angle triangle. So if this is B, okay, I know that the sum of these two angles has to be pi over 2 radians. Okay, because the sum of all three angles, again, we normally think of that as 180 degrees, but it's pi radians. And if this is pi over 2 radians, then the sum of these two has to be pi over 2. So this angle here is just going to be pi over 2 minus whatever B is. Okay, but now I've got a straight line here. So I know the angle all the way across this straight line is going to be pi radians. I already know that this is pi over 2, so the sum of these two angles has to be pi over 2. So this angle here is just pi over 2 minus this angle there, pi over 2 minus B. But what's that equal to? Hey, pi over 2 minus pi over 2 is 0, so I'm just left with negative of negative B. So it turns out that this angle inside is also B. So it turns out that this triangle here is just similar to that one there. Okay? Because if they share two angles, then they must share the third. But that's not really the important part. And the important part is that now I can fill out the side lengths here. Okay, so let's start with the opposite side here. So let's remember it's the hypotenuse, which is sine A, times the sine of the angle, which is B. So this here is sine A sine B, this little portion there. And this one here is going to be the hypotenuse, sine A, times the cosine of the angle. So this is going to be sine A cos B. All right, so let's keep going. Let's now come to this large triangle here. It's the last one we have to do. Now there's a few ways in which we can get an angle. I notice here that this angle is complementary to A plus B. So I can write this as pi over 2 minus A plus B. But I actually have another really nice property. Two parallel lines, the bases of this rectangle, that's being crossed by this line here. So I can use my parallel line principle. A plus B, this angle, has to be equal to that angle there by my parallel line principle. And so I can just say that this is A plus B. Now this is very nice because remember we talked about compound angles as being the sums or differences. And we're trying to find trig ratios of those. So let's now work with this right angle triangle, which again has hypotenuse of 1. So if I'm looking for this side, well, it's just the hypotenuse times the sine of the angle. So that's just going to be sine of A plus B. All right. This is just going to be the hypotenuse times the cosine of the angle. So that's just going to be 1 times cos of A plus B. So this is cos of A plus B. But now that we have everything filled out, I think we actually have some nice stuff that's going to happen. Because let's look at this side of the rectangle as sine of A plus B, the same length as that side of the rectangle, which is made up of these two parts. So what have we just shown? We've shown that sine of A plus B is equal to sine of A times cos of B plus cos of A times sine of B. And there we have a property for the sine of the sum of two angles. Now what's nice about this identity is that I'm working with the angle A plus B on the left, but all the expressions on the right, well, involve the individual angles. And that's ideally what we'd like to have, is we'd like to have an identity where the right-hand side has all of the individual angles. Now, by the way, what this also shows is that sine of A plus B is not equal to sine of A plus sine of B. In fact, if you want to test that out, you can pick an example and you'll see very clearly that sine of A plus B is not equal to the sine of A plus sine of B. That would be great, but doesn't happen. It's actually equal to this expression here. But we are actually going to get more out of this diagram, because we see cos of A plus B, well, isn't equal to this whole side, okay? But it's equal to the whole side length of the rectangle, which is equal to cos A cos B, minus this little portion here, sine A sine B. So we in fact also get a formula for cos of A plus B. So that's going to be the whole length of the rectangle, cos A cos B, minus this little portion here, sine A sine B. And what we have now is a second identity that gives us another way of writing the cosine of the sum of two angles. All right. Now, in terms of the way I interpret this, as I always think of this, instead of A's and B's, I think of the first angle and the second angle. So I try to remember this as sine of the first times cos of the second, plus cos of the first times sine of the second. I think of this as cos of the first times cos of the second, minus sine of the first, sine of the second. And try to remember that sine has the same operation. Cosine will have the opposite operation. All right? So now, let's take a quick look at how we can apply this formula, at least one of these. Is I'm asking you to determine the exact value of sine of 5 pi over 12. And you might say to yourself, well, 5 pi over 12 is not a special angle. Okay? So you would think you couldn't do it. But what if we tried to relate this angle to some special angles through addition? Okay? So let's think of our special angles. Well, we know we have pi over 6, pi over 4, pi over 3. But in order to find these connections, it's a lot easier if I work with the same denominators. So let's change these all into denominator 12. This is 2 pi over 12. Okay, this is 3 pi over 12, and the last one is 4 pi over 12. And what I realize is that 5 pi over 12 can be written as the sum of pi over 6 plus pi over 4. Okay, because that's 2 pi over 12 plus 3 pi over 12 gives me 5 pi over 12. So I can rewrite this angle as the sum of two special angles. All right? But now look at what we can do. We can now rewrite this using our new formula in terms of sines and cosines of the individual angles, both of which are special angles. So this is where you might want to stop the video and figure this out on your own and see how far you can get. Okay, so I'll be back in a sec. Okay, so we're back here, and let's apply our formula, see what happens. So this one here, so this is going to be equal to sine of the first angle times cos of the second angle plus cos of the first times sine of the second. Okay, now maybe you know these by heart by now, or you might want to draw yourself a little diagram. So pi over 6 looks something like this, 1, 2, root 3, and then pi over 4, again, both in the first quadrant. So 1, 1, root 2, and the diagram means you can just read the answers right off. So sine of pi over 6 is 1 over 2. Cos of pi over 4 is 1 over root 2, plus cos of pi over 6 root 3 over 2, times sine of pi over 4, 1 over root 2. And now we just have to simplify. So this is 1 over 2 root 2 plus root 3 over 2 root 2 okay, which gives us 1 plus root 3 over 2 root 2. And I'm actually happy to accept this as a final answer, but if you did want to rationalize the denominator, let's just multiply numerator and denominator by root 2. So this gives us root 2 plus root 2 times root 3 is root 6 over, well, root 2 times root 2 is 2, times the other 2 is 4, and there's our final answer. And if you wanted to check your answer, you could put sine of 5 pi over 12 in your calculator and get an answer, get an approximation, and then take an approximation of this sum here, and you'll see that they are the same. Okay? Now this is certainly not the most important use of these formulas, but it is, nice example on how we can apply them. All right? So let's go to our next page now and see that these formulas actually do a lot more for us. Because if I have a formula for sine of a plus b, why not have a formula for sine of a minus b? Okay, or cos a minus b. And I think these will also help us determine formulas for maybe sine 2a, cos 2a. So instead of starting from scratch, we're going to try to see if we can use the ones we already have. And just to get you started, is what I already have is a formula for the sine of a sum. So the question is can I write this as a sum? Can I write this as a sum? Well, how can we do that? And I'll start you off with the first one, is I can rewrite sine of a minus b as sine of a plus negative b. Okay? And now I can apply the formula we just found. And you could do something similar with all the other ones. So I'll ask you to try all the way up to cos 2a. Okay? Remember that I want all your answers in terms of sine A, sine B, cos A, cos B. No negatives in there. So little tip, you may want to use some of our earlier identities to do some simplification. Okay? And another thing I'll let you know is that for cos 2a, I'm claiming that there's 3 possible answers for this one here. A little tip, you might have to use one of your grade 11 identities for that. All right, so here you might want to stop the video and work on them on your own. Okay, and we'll be back to take them up. All right, so we're back here, and let's see what happens when I apply my formulas to this here. All right, so let me just apply the formula. So it's sine of the first times cos of the second, but remember this is minus b now, plus cos of the first times sine of the second, which again is minus b, right? Now, this is where we have to go back to some of our old identities. And what we found were relationships between sine and cosine of some angle and the negative of that angle. And remember, we said that the cosine values would be equal and the sine values would be negatives of each other. Okay, our related angle identities. So cos of negative b is actually the same as cos of b. And sine of negative b is the negative of the sine of b. And there you go. So now we've managed to write sine of a minus b in terms of trig ratios of the individual angles. And of course, we'll just clean this up. We're adding a negative there. So this gives us sine a cos b minus cos a sine b. You might have even guessed that this would be the final answer. Okay, similarly here, we're going to do the same thing. We're going to rewrite this as cos of a plus negative b. So that means now we can apply our compound angle for cosine. So cos a cos negative b minus sine a sine of negative b. And again, we're going to use these same related angle identities to give us cos a cos b. Okay, this is going to be equal to minus sine a negative sine b. And so again, clean this up with the negatives, so we end up with cos a cos b plus sine a sine b. And we see that same pattern before, that with the sines, the operation is the same. With the cosines, the operations are opposite. Okay, Let's take a look at sine 2a. Well, again, I'm going to write this as a sum, as a plus a. So now I can apply my formula. Sine of the first times cos of the second, which happens to be the exact same angle, plus cos of the first times sine of the second. And this is where we realize, hey, these two expressions are exactly the same since multiplication is commutative. So I can just flip that around, and this becomes 2 sine a cos a. There we go. This is what we call the double angle formula for sine. Let's do the same thing for cos 2a. Let's rewrite that as cos of a plus a. So that gives me cos of the first, cos of the second, minus sine of the first, sine of the second. And lo and behold, we have cos squared a minus sine squared a. Right? So this is one of our three options. Okay? But, and this is where cos 2a is very nice, is I see cos squared a and sine squared a, and I remember that we have that Pythagorean identity that relates the squares of cosine and sine. Okay, so what I'm going to do here is I'm going to, in our first option, rewrite cosine squared a as 1 minus sine squared. So what does that give us? It gives us 1 minus sine squared a minus that other sine squared a. Okay, and now we can simplify that to 1 minus 2 sine squared a. And there's another version of our double angle formula. Now what's nice about this one here is it only contains sine of a. Okay, we can do the same thing here, but this time change the cosine. Okay, here, change the sine squared a into 1 minus cosine. So here we've got cos squared a. I'll leave that one the same minus. And now here, I'm just going to replace sine squared a by 1 minus cos squared a. And let's see what we have. Well, we have cos squared a plus cos squared a. So 2 cos squared a. And then here we have minus 1. So there's our third version of that identity. Okay? So this now adds to the list of all our identities. Now this last problem I think we'll just do together. And again, this is a pretty common type of problem in that it's a good exercise in using our compound angle formulas and also using our knowledge of these trig ratios. So let's see what they tell us. Notice that they don't tell us what x is as an angle, but they do tell us that it's in the first quadrant because it's between 0 and pi over 2, and they tell us its sine value. So let's draw ourselves a little diagram here. I know I have some angle, okay, x in the first quadrant, and I know the sine value is 4 over 5. And then for the other one, well, they don't tell me what y is, but they do tell me that it's in, well, this would be in the fourth quadrant. All right. And they give me its sine value also. Not surprisingly, it's negative, so it's in the fourth quadrant. And what they want us to do is they want us to determine cos of x minus y. Well, all my information is given in terms of x and y individually. So it makes a lot of sense to apply our compound angle formula here. So this can be rewritten as cos x cos y. Okay, remember opposite sign for cosine, plus sine x sine y. Now, I already know what sine x and sine y are equal to. They gave them to me. I know that this is 4 over 5, and I know that this is negative 12 over 13. Okay, question is what's cos x and cos y going to be equal to? I don't know what those angles are. By the way, I didn't specify here, but I am looking for the exact answer. So we can't use our inverse sine here on our calculator. Just in case you think of doing that, that would make sense. But if I'm looking for an exact answer, that's not going to be helpful. Okay, but this is where we remember that sine x is defined as my y value over my r value. So let's add that into our equation. My r value is 5, and in this case here, my y value okay, is going to be 4. But that means I can now determine my x value using Pythagoras. Because remember that x squared plus y squared equals my r squared. So this is just going to be equal to 5 squared minus 4 squared, which you probably already knew was going to be square root of 9, which is 3. So now I can calculate cos x, 3 over 5. Okay, I can do the same thing with this angle here. I know sine of y, so I know that the r value has to be 13, since it's got to be positive, and the y value has to be negative 12. So if I want to calculate the x value, it's again just the square root of 13 squared minus negative 12 squared. So 169 minus 144 is 25, so that's just going to be equal to 5. And so now I can find the cosine value, which is just going to be 5 over 13. All right, and now we can calculate our answer, or simplify our answer. So this will be, so since I want to keep the same denominator, I'm not going to bother canceling out these 5s because there's nothing to cancel out in the second one. So I'll keep this as 15 over, so that's 50 plus 15 is 65, okay, minus, this will be 48 over 65. So our final answer is going to be, so 48 minus 15, 48, 38, 33, so negative 33 over 65. Okay, and we were able to determine the exact value of this expression without ever knowing what the angles x and y actually were. All right, so again, like I said, this is a pretty typical type of example that uses all these pieces of information. Okay, so in the end, the important thing to get out of this lesson really is all the compound angle formulas which we achieved. So our compound angle formulas for sine and cosine when we're adding the angles, when we're subtracting the angles, and probably the most important out of all of them will be these double angle formulas. These are probably the ones you're going to come across most often, and in particular, remember that cos 2a has these 3 options, and you'll find that sometimes one is preferable to the others. All right, and that's it for this very long lesson.